Hello and welcome back to KustoCon 2024. Hey Alex, nice to see you all back and bearing with us this late in the evening or this early in the morning, depending on where you are. And the next session is Find Lateral Movement Path using KQL Graph Semantics. But before we start with that, thank you again to our amazing sponsors to making this all possible today. Without this, such events wouldn't be possible and it wouldn't be able to do this for free. Quick, who am I? My name is Fabian Bader and I work as a cybersecurity architect at Glückania in Germany. I have a blog where you can also find a lot of the information I will share today. That is cloudbrothers.info, and you will also find me on social media under Fabian_Bader. And with that, let's get started. Graph semantics, you might ask yourself. If you haven't followed yet along, you think when you hear Microsoft and Graph about Microsoft Graph, this nice way of requesting data from Entra ID and Exchange Online and all the other stuff that is using Graph. But this is not what I mean when I'm talking graph semantics in Kusto today. So basically, graph semantics in Kusto are based on graph theory. That is a way in mathematics to describe certain relations and objects within their own way of how they interact with each other. So there is the concept of verticals, also called nodes, and this is what we will use today, and how they are connected. And those connections are called edges. And those connections between certain nodes, those edges, they can be used in mathematical queries to find the shortest way between two nodes, depending on what edges are in between. And to break this down out of the complete theory and a bit more things where we can understand it, I visualize something here. We have a user A on the top left-hand side, and we have a computer 1 on the right-hand side. And as well, we have on the left bottom a group Z. All those are nodes in our graph. Now let's take a look on what edges we have. We have one edge from the user A going down to group Z, and this edge is the type member of. So the user A is member of group Z. Then we have an additional edge, and this is user A is admin to computer 1. In Windows terms, this means he's member of the local admin group, but we want to use similar terminology that is used within Bloodhound, one of the most famous graph tools out there for red and purple teaming. And there the edge is called admin2. This means user A has administrative control over computer 1. And the last edge that we have in this picture is this one. This goes from computer 1 to user A and is called head session. This means that on this computer, user A was logged in. Therefore, computer 1 had a session of user A. Let's break that down in a bit more how we can use this example. And before we do this, let's talk about Bloodhound. Because for a long time, red teamers were the only one using graph at all. So they identified paths to something like the domain admin in your environment by querying a lot of data, most likely from Active Directory. And then they used the graph notations and ciphers, so query language stuff, to find a way from a compromised user up to something like the domain admin. But when we want to visualize something like that, we again have to use something we had before, nodes and the edges. And on the left-hand side, again, we have our user A with the admin2 edge to computer 1. And now we have also user B. And computer 1 has an edge to the node user B from the type head session. So this means, consequently, that user A has administrative privileges on computer 1, which had a session of user B. Depending on the configuration and the protection of computer A, this means that user A can compromise the credentials of user B. Because user A is administrator, so they could install something like a keylogger, they could dump the LSS process of this Windows machine, or do whatever they like on this machine because they have administrative privileges. And since user B has signed in onto this machine, their credentials are now at risk. This is a very simple and very easy lateral movement path. We have just two users, one computer. This can be done really, really easy, even with like a pen and paper. But what if this gets more complicated? So now when we look at this, this is a much more complicated picture. We no longer have just user A and user B, but now we have user F, we have computer 5, and a lot of edges in between. And if we wanted to query this data in something like Custo with just something like regular joins, this would not be possible. The one before that we have seen, this is very easy, and you could combine the two data sets using just something like an inner join or an outer join and fiddle with the where clauses. But as soon as we have more hops than one, like in this picture, those joins just won't do the difference. So since the join operator itself is too limiting and too complex to use, there is something even better, and this is graph pattern. Now let's have a look at how the Custo query language is using graph pattern at the moment. Down here we have a lateral movement path, and it again starts on the left-hand side with an account and ends with an account. And the idea is that we have a compromised account on the left-hand side, multiple nodes and edges in between, and they change, as you can see. We have admin2, we have has session, all this stuff, up until the last account, which would be our domain admin. And to find something like this, we can use a query or a graph syntax like the one I'm just showing on here. So on the left-hand side, you have in brackets the account node. Nodes are always represented using brackets. Then you have an arrow-like ASCII character with a has path through. So this means that we have now another type of object in here, which is the edge, and we named it has path through. And on the right-hand side, again in brackets, we have the administrator. And this is a node. So we have on the left-hand side one node, on the right-hand side one node, and in between we just defined that there has to be an edge between those nodes. Actually, this exact query would not work like this, but we will see this in a minute. Now, you have seen down there the lateral movement path. Let's map this on our initial query. So if we remove all the information that is not important for our actual lateral movement path, you will see we now have account on the left-hand side, computer 1 going up to admin on the right-hand side, and all those nodes and edges in between we have to somehow query and create. Before we look into the demo that I prepared, let's talk a bit more about nodes and properties in KQL. Because so far I always named the nodes something like computer1 or admin, but of course those names would be very much problematic in an environment where there is more than one user named admin or one or more computers named computer1. For that reason, it's very important that we don't use such ambiguous names, but use something more unique. And for that, I would recommend that we use something like the hash function and make sure that the casing of what we hash is always the same and create our own node ID. Hash itself might not be enough. Maybe you want to use hash many to create something out of computer name and domain name and get a unique identifier for node ID this way. Now, since we created our node ID, which is something like 2594 whatever, we still want to use computer1 as a marker, as a property, because at least I wouldn't be able to recognize this node ID out of hundreds of others and be sure that, oh yeah, this is computer1. So what we can do is that we add certain properties. This could be something like a node display name. I just named it this way. You can name it whatever you like. Or an object type. Maybe you have different types of objects that you have in your graph. Then it is important to make a difference. Is it a device? Is it a user? Is it whatever? Maybe you want to also add information about where this resource is located, like the resource group, if it's in Azure, or it has an on-prem SID, or it has a distinguished name, and you want to have this in there to easily later on find this particular computer, or use it even for filtering. So as you can see, in your graph, one node must not be just one property, but you can add multiple ones in here. So, do you want to build some nodes with me? Then let's head over to our actual first demo. I'm in here in the advanced hunting dialog, and let me just try to make the most out of this screen estate, and I hope most of you can read it. So what I did here is I am using the identity info, and the keen-eyed among you will find that this is not the actual identity info, but it's the identity info demo. So I cheated a bit and created a function that will return exactly the data that I wanted to return, making this demo hopefully error-free. And what I'm doing here is I'm querying the information that is stored in XDR in the identity info table. I'm removing everything where I don't have an on-prem SID. Make sure that this fits your query you want to do. Since I want to find a lateral movement on-prem, I'm not very interested in any identities that are cloud only at the moment. But if you want to do something with cloud identities, and you don't have synced accounts, especially for administrators, I hope you don't have them, then don't use that exact filtering, of course. And then in the next line, I'm doing a summarize argmax based on the timestamp and add the properties tags, distinguished name, and summarize this by account name and on-prem SID. Then I rename on-prem SID to account SID and create the node ID. Therefore, I'm using the hash many, and the first property I put in here is the account name, then the account SID, This way I'm making sure that even if the account name is exactly the same, it will be different node ID because the account SID itself cannot be the same twice. And then I'm also adding a property node display name where I use the account name for, and I add an object type identity. So this is just made up, but this way now I have a temp table, temp identity info. This is all my identities in my environment, or at least all on-premises identities. Next, I want to have all my devices. For this, I'm using again the device info demo table and summarize based on timestamp, device name by device ID, just getting the latest information about the device. Create my own node ID again with the hash many, this time using device name and device ID as properties for this hash algorithm, and then just putting out node ID, device name, creating a node display name property and object type from the type device. And then I put both of those tables that I just created in a new table called nodes. And when I run this, let me just show you what we get. We now have a list of all the computers in my demo environment. And if I scroll down here, also all the identities. As you can see, this is a small demo environment. We have about 43 items in here. Of course, in a real-world scenario, we would have hundreds, thousands, or even more entities or nodes in here. You can see that for the device type, we have the device ID, we have the device name, node display name, and the object type. Everything else, all other properties are empty. For identities, we have the node ID, then the node display name, and over here we now have also additional information, the account name, let me just switch that over, account SID, timestamp, tags, and the distinguished name. Tags is really nice. This is something Microsoft Defender for Identity will provide you in the identity info table by default, and there you can see there are certain accounts tagged as sensitive. This we will later use for filtering, just so that you heard where this information is coming from. All right, so now we have built our own node database. This is basically the basis of everything else we want to do, but we have our nodes, but how are they interacting? We have seen that there has to be some connection between them, and that's the way how we have to create bridges, or let's call them edges. Let me just switch over to the next query in here. And this is the second query. And here I used some information and query material that is available publicly in the Falcon Hound project, a project that is using the XDR data and sending it over to Bloodhound. But we don't want to send any data anywhere else. We want to keep it in our XDR experience, but just a call out to this really cool project. We have an exclude SID here. We will talk about this in a second. But first, let's create edges. And for that, we have the device info edge. We are using the device info table, a bit prepared for this demo. Then we look in the device info for logged on users and for their username and the SID, and put them as separate properties in here. Then remove everything where there is no SID, because we cannot match that up later on. And now we have a property called source node ID, where we use the hash many. And if you followed, when we are creating the nodes, we use this to create the unique node ID. And that is exactly what we recreate here. So in this case, you can see that we create source based on the device name and the device ID, meaning that the source node is a device and the destination node is based on account and account SID, so meaning an identity. Then, after we did add those information, we summarize by source node ID, destination node ID, device name, and account SID, and add a new field called edge display name, which is just the device name from where it originated, so the source, and the edge type, which we name head session. Then, since the device info is only one of our data sources, we also look at the device lock-on events. And in this case, we look into which accounts had a lock-on success action. This was not negotiated and was not from the type network or service. So this means this account actually signed in onto this machine using either RDP or interactive on the console or the laptop itself. Then again, we clean up all the devices or accounts we cannot match, remove the accounts based on the exclude SID up here, and this is just accounts that are built into Windows, like the desktop manager and such, we don't want to have in here. Then we build a summarize based on this information, and then add again source node ID and destination node ID. Again, we also start from a device to an identity, and this is also a head session edge type. The next one we then create is using this information we just had, all sessions, and look into the last day. Again, this is a bit changed for this demo, and add another edge type has session, meaning head session is like 30 days back or longer. Has session is everything that happened in the last 24 hours. Now we want to have also the information who is administrator on which machine, and for that we're using the device lock-on event table, looking for lock-on success, and is local admin true, or 1 in this case. Microsoft XDR is already providing us this information, making it really easy to get this. And then we summarize, create a source and destination node ID. In this case, it's an edge starting from an account to a device, from an identity to a device, and we name it admin2. And at the end, we combine all this information into a long list of edges, and as you can see here, we now have multiple edges, in total 29, and they have different edge types in here. So when we look at the first one, this is the account Fabian, and the source node ID in this case is the L870, and it has an head session from this user. Now we have built our nodes, and we created all the different edges that we wanted. This would be edge admin2, admin has session, and head session from different data sets. So all this information that we just created, we have Takeshi, desktop, and an Edtra Connect server in our data set. And then we have in the middle something called admin tier violator. As some of you might already have guessed, this is the person or the account that is problematic in our environment. And then we also have our domain admin. To better look at the path that we want to go between those. We have the edges in here. So Takeshi is administrator to a desktop computer. So he's a local admin on his machine. The account ADM tier validator is also admin on this machine, but also there's a session from this user on this desktop. So there was a head session edge to this tier validator. This account is also admin to the Entra Connect server, and he also had a session on this. And then we had the domain admin, who was also signed into the Entra Connect server, and of course the domain admin is admin to all the devices, and of course users. That we don't have to do this work ourselves and find all those nodes and edges ourselves, we now can use the graph operators. Finally, we are here, and there are actually just 3 at the moment. We have make graph, which can be used to build the actual graph in real time. We have the graph match. This can be used to search the graph that was created by make graph and get the data that we want to get out of it. And there is graph to table, because when we just would try to output make graph, this would not work. And with graph to table, we can check if all the data in our graph is there and valid. Let's get back to our demo. So up here, we have all the different nodes and edges and everything that we just gone through. And now we come down here. And this is our first step, creating our graph. We take our edges and in the next line call the make graph operator. But now we have to tell the make graph operator on how to build the actual graph. And in this case, we say the source node ID has an edge to the destination node ID, both properties in the edges table, and we will use the nodes table on node ID for either source node ID or destination node ID and combine those two as a graph. If I would just run this like this, we will get an error and there is, sorry, you have to use something like graph match or graph to table to actually show this data. Then let's do this. Let's use graph to table, and we want to see all the nodes. And there you can see we have now our node IDs, device IDs, whatever, identities and everything in here. So this is the list of nodes we have. And we can do the same with graph to table for edges. And after a few seconds, we should have a full list of all our edges. But it's still loading, and there it is. And again, we have source node ID, destination node ID. Not that different from what we have put in, but this was expected because it's a very simple way of outputting the data. What we really want to do is we want to query the graph information. And you can already read it. The first example I'm going to do, this will fail, and it will not find anything. And I will explain why that is. So what we do is we do a graph match and tell it again we want to have a node that I name account, and this name you can choose whatever you like, and then has an edge, has passed to administrator. And with that, I'm defining that This node has to have a direct edge to this node, and there cannot be anything in between. But as we have seen before, this is not how our data is built. So we have at least a few hops in between, a few nodes in between. And this is why we are going to use a bit of a different way of writing this. And we will say, I want to have the node account, and it has to have an edge that is either 4 or 5 edges long. So the length in between those nodes must be 4 or 5 until we reach administrator. You can play around with this. Don't go too high at the beginning because it can break, especially in larger environments, your query. And this is just on how big and long the combination between nodes and edges is between the starting node and the end node. Now we have this edge called hasPass2. But of course, just the name itself wouldn't be anything in here. KQL does not know what hasPass2 means. So what I have in the next is I have filtering. And with the first filter, I define that hasPass2 edge type has to be either hasSession, headSession, or admin2. One of those three is okay, and then we can have this combination here. Then for the administrator node, I also define administrator account name must start with T0. So this is the naming that I have in my domain. If you want to use something more broadly usable, you could say tags has sensitive, making sure that the tag sensitive is available for this node. So this means administrator could also be something like bunny, and I just have to replace administrator with bunny all the way down here in my query. Next, I want to define what is the source account. And for that, I again say, okay, my source object type has to be an identity, and my source cannot be the same as the administrator. This way I can prevent circles and stuff like that. And last but not least, I have hasPass2 source node ID cannot be the destination node ID. Again, trying to prevent certain loops. This all here is required by the make graph match operator, so we need a where with at least one filter. The next thing that is required is the project, because if we would just run it like this without the project, this will also fail, because for the graph match operator, project is a required attribute, and we now say we want to have the user, which is the node or the property account name of the node account. We want to have a property path that is based on the edge display name from the edges. Then we want to have the edge type. And last but not least, we want to have the account name of the node administrator as property domain admin. And if I run this, you remember, first I ran it without the variable length edges. There were no results, but now there are 24 results. And when we have a look here, we can see there is the user Takeshi Kovac, that there is another node, desktop, there's the node admin tier violator, and a node called AADC01, which would be the Entra Connect server. And then, last but not least, we have the node tier 0 Fabian, which would be the domain admin. Then we have the different edges in between, like admin2, head session, admin2, head session. Let us clean this up a bit and add a few additional information. So what I want to find out is how long is the path, and I don't want to have anything where the user is ADM tier violator. That is just to make it a bit more convenient to read in here. Now we only have 4 items left, and you can see it's always starting with the user Takeshi Kovac, and it always ends with the tier 0 Fabian account. And yeah, you now think, okay, those are the exact same path. And that is mostly right, but there are a few differences. If we have a look, in this case we have the Takeshi Kovac node is admin to this user, this computer, which has a session of admin tier violator, which is admin to this computer, and this computer had a session of this. And this is exactly where it differs. Here it is had session, has session. So since we have 2 edges that are almost the same, but not exactly the same, we now have duplicates in here. That points to reason if this edge is even really helpful. And I think for just finding a lateral movement path from A to B, this is not really helpful. If you want to know if this path is still active because it still was used or signed in the last few days, then this could be helpful. All right, so we had this before. We have gone through the different graph operators you can use. And now let's look again at this picture on how this would pan out as a lateral movement path. And this is exactly what we have here. We had the Takeshi, admin to desktop, had session to the admin tier violator. This one was admin to Entra Connect, and this had an session from the domain admin. And that was the way a regular user without any permissions on Entra Connect or in the domain could take over your whole domain. Basically what Bloodhound does as well, but natively in KQL with all the information that XDR Microsoft is already presenting to you. And in the blog post that I published on this, I also added a little gimmick. And this is, since all this information down here is really hard to read, I added a bit of some fun KQL to build the lateral movement path as an ASCII art. So now you can see that a bit more easily in here. Of course, it's not the same as you have seen before in the presentation. It's not that nice looking, but it's Takeshi is admin to desktop, had session from tier violator, which is admin to this computer, and this computer had a session from user tier 0 Fabian. And just to show you one last trick, this would be now again, you don't know what's the naming of the account in your domain account, the domain admin accounts in your environment is, then use the tag sensitive, and this will not only give you domain admin accounts but also other stuff. In my case, it will result in the same lateral movement path as before. All right, so before I close up, you might have seen the left screenshot already in your environment, the so-called attack surface map by Microsoft. Behind this is the extended security posture management of Microsoft, where based on things like critical assets, they will build lateral movement paths or attack surfaces, and this almost looks like something Bloodhound would produce. We have nodes, we have edges, and when you zoom in a bit, you will see that there is like frequently logged in by and all this information. So they are named a bit different, but Microsoft has this information. since we want to do this not in a graphical way, but in a custom way, let's have a look on how you can use the data yourself. And this is with two very nice tables Microsoft is presenting in the advanced hunting. We have the exposure graph nodes, and when we just have a look here, this is a list of all the nodes that are either devices, that's why I filtered, or users in my environment. And as you can see, Microsoft now has already taken some of the work I did manually before and created this for you. And there's even more information in here than what we have in the other one. If you look at something like, let's go down here and use one of the devices. Sorted like this. We can see that there are node properties, and in this node properties we have raw data. And this is really, really nice. You have stuff like high-risk vulnerability insights, where you can see is there something not patched on this machine. You can see what is it first seen, last seen, is it a server or is it an end device, which version is it domain joined. You have stuff like the RDP status, which is showing is the service for RDP running on this machine, and is it allowing connections, and also other information like is there WMI running, WinRM running. So this is really, really helpful for mapping out your environment without much of own work, because you can use what Microsoft is already presenting you in those tables. And it's not that you only have the nodes, but Microsoft is also offering you the edges for that. This will take a bit longer, and for some reason it didn't take into account my target node label, or did it? Yes, it did, but it's a long list, and you can see there's stuff like source node CVE, and here we have user, has role on, can authenticate to, affecting security configurations. So there are a lot more edges than what I created before. And of course, you can query them the same way with the graph match as you have seen me querying the data before. And this data set is really, really helpful and growing every few months. Microsoft is heavily investing here. Most of you will see this first in the exposure management over here, but using the raw data that is available in advanced hunting can be super helpful. And if we do a distinct on the node labels, you will see that there's a lot more in here than just the devices and users I showed before. There is information about CVEs. We have AWS if it's connected to Defender for Cloud. We have managed identities in here, key vaults. So a lot more information, a lot more to query, and this makes this a real treasure trove of information that you can use in your queries to find lateral movement paths or to do threat hunting. With this, I will thank you for your time. I hope that you learned a bit about the graph semantics in KQL, and I wish you a lot of fun with the last two sessions of this evening. Thank you so much.